Hello Math 152 students. In this video, we'll take a look at wrapping up the Reese's Pieces example and then getting to our formulas and some StatCrunch in 8.2. So we were looking at the example of 20 candies at a time, and we did multiple samples. Here I had to generate a new one, so it looks a little different. But this time, we're going to see what happens as our sample size, which is our number of candies in each sample, increases. So I'm going to start by doing one sample and illustrate that, but I want to do 50 candies in that sample. So I'm going to ask it to animate one, and then we'll speed up the process. So I turn out 50 candies. We're going to calculate the proportion of orange and plot that just like before. Notice on your x-axis, they've spaced it out a little bit differently, but you could still have anywhere between 0% orange and 100%, but it's not as likely maybe that we're going to see those extremes. So notice in this example, we're seeing a p-hat of 0.44, and we've got that plotted. Let's go ahead and I'm going to do 100 samples at a time. Take off my animate, quickly turn them out, and plot 100. Let's plot 100 more. Okay, so notice what happens. This looks a whole lot more normal than my previous examples. And just kind of for good measure, let's go one more time. Let's say I were to take a sample of 75. Okay. Animate the first one and observe as we talk. I could still have between 0 and 100% orange, but I'm probably not going to see as much variability in that sample proportion. And notice this time I see 0.6. Ooh, that's kind of on the high side. Let's go ahead and do 100 samples. We'll animate it and see what happens with those numbers. So notice that 0.6 I noticed was high. It's one of the higher numbers to see. Looks like a lot of our numbers are close to 0.5. We're going to see some spikes at different places depending on the specific samples that we get. All right, so what are we seeing in this case? Well, when I up my number of candies, I get a curve that looks more normal compared to my 50, compared to my 10, compared to, I think, my 20 as well. So we're going to see kind of the same thing that was going on in 8.1. As our N increases, our number of individuals, or candies in this case, and the sample increases, our sampling distribution is going to look different. Now, our conditions are going to be a little different from 8.2, and one of the tricky parts is to identify which set of conditions to use and apply them properly. So it's not just going to depend on our sample size, it also depends on your proportion. So let's go ahead and go back to our slides and sum up some of the things that we've seen. Under some conditions, our p-hat is going to have a normal distribution. And the first condition that we're going to have to check out, instead of just looking at the n, is a combination of the n times p times 1 minus p. Now you might say, hey, this first condition, n times p times 1 minus p is bigger than or equal to 10, greater than or equal to 10. Well, we've seen that condition, and that's correct. We've seen this exact condition in the binomial. Part of the reason we're seeing this condition again is the p-hat, or the sample proportion, is based on the binomial. Each candy could be orange or not, success or failure. And then we take the number of successes, the number of oranges, and divide by our sample size to create a p-hat. So the sample distribution, or the sampling distribution for the sample proportion, kind of a mouthful there, is based on a binomial. This is the condition for the binomial to be approximately normal, which means that if the binomial is approximately normal, the p-hats will be. Then the second one is that your sample should not be more than 5% of your population. Now this applies when you have a finite population, not an infinite. It's a little bit harder to see in the Reese's example because the population of all Reese's Pieces Well, that's a whole lot. All the Reese's Pieces ever produced. It almost feels infinite, even though we're not exactly infinite. But what I mean by it makes better sense in other contexts is if you are sampling people in the United States. The United States has a finite population. We could Google that. And we wouldn't want our sample to be more than 5% of that total population. So again, it makes more sense when we're talking about actual samples, something a little bit more concrete. For the why part, well, part of it is we want to make sure our sample is independent. In other words, this 5% ties back to the binomial, and in the binomial we had to have independent trials, meaning one person or one trial doesn't affect the next. If we start getting too large of a sample compared to our population, we're going to run into some problems with the independence and the one person affecting the next. So most of the time, in reality, your samples are going to be relatively small compared to your population. It's rare that you would even try to get a sample of more than 5%. For example, if we're talking about college students in the US and sampling from those, we probably have several million college students. And 5% of several million is still a lot. If we were thinking about surveying CVCC students, we might look at maybe about the total population being somewhere in the neighborhood of 5,000 students, depending on semester to semester and who we include in that group. But let's say we have 5,000 CVCC students. Well, 5% is still quite a bit. Let's see, if we had 5,000, 10% would be 500, 5% would be 250. That's still a decent sized sample, but that would kind of limit how many samples you would want to collect, or what your sample size would be for your sample. So if these two conditions are met, then we can say that our p-hats are normally distributed. So going back to our app here, we were dealing with different values of n. Our highest was 75, and our p that we were assuming was a 50% proportion of orange. If we were to do n times p times 1 minus p for the 75, that one turns out bigger than 10, just plugging into that formula. But in the event where we were doing 10 at a time, that one actually didn't satisfy the condition. We would see some issues when that sample size got too small. So let's go back to those slides and look at our formulas. Conditions are met, we have p-hat is normally distributed, and there's two formulas, one for the mean and one for the standard deviation. The standard deviation formula is sort of similar to the 8.1 in that we have a part up here divided by the square root of n. If you think back to your binomial distribution, the standard deviation for a binomial was the square root of p times 1 minus p. So here we're seeing the standard deviation for a binomial divided by our square root of n. It's kind of the same concept as what we saw in 8.1, but it's a little bit harder to put into practice. Part of the reason is we're going to see some decimals. Sometimes it's easy to make a typo or some calculation mistakes with this standard deviation. So we'll see an example in a second, but the other formula is that the mean of the p-hats is equal to p. This p is the population proportion. What it means is that all of the sample proportions are going to have a center that matches the center of your population. Same concept as 8.1, just different symbols and different terms. So let's look at a specific example and see how this applies. According to the Center for Disease Control and Prevention, 18.8% of children ages 6 through 11 years old were overweight in 2004. So notice my context gives me a percent, which we can think about a percent as translating into a proportion. We'll just kind of go back and forth between the two, whichever makes more sense to actually use in the context of our problem. A lot of times when we're describing, we'll use a percent, but in our calculations, we'll turn it into a proportion. So then let's suppose we obtain a random sample of 90 children ages 6 through 11. Describe the sampling distribution of the sample proportion of the overweight children. Again, in these examples, they're going to sound kind of wordy, but describing the sampling distribution for the sample proportion means we want to give the shape, the center, and the spread, or the shape, the mean, and the standard deviation. The other thing I want us to note is that we were given a sample size of 90 children, meaning now we have an N and we can find a P. So before we go ahead and give the shape, we want to check our conditions. So the first thing we'll check is that less than 5%. There are probably several million children 6 through 11 in the US, or there were in 2004, definitely. So 90 is definitely less than 5% of your population size. We're good there. Then for the N minus P times 1 minus P, plug in your 90, plug in the proportion form, the decimal, and calculate. So just chunk this bit into your calculator. You get 13.7, which is bigger than 10. We're good to go. So what that means is our sample proportion, our p-hat, is approximately normal. The mean of our p-hats matches the mean of our underlying distribution at 18.8% or 0.188. And for the standard deviation, we need to plug into this formula. One of the things to be cautious with in your calculator is make sure you're taking the square root of this entire quotient. Use your parentheses so that this entire fraction is under the square root. Just be a little bit careful and double check this calculation to make sure you can reproduce this standard deviation. Sometimes the problems in 8.2 are really calculator input errors at the standard deviation point. So once we calculate the standard deviation, it's pretty small. And one of the things we want to notice in chapter 8 is that this mean and standard deviation are going to be decimals. Our mean can't be over 1 because our proportion can't be over 1. Therefore, our standard deviations are usually going to be pretty small, and this can lend itself to more round-off error. So it's also important in 8.2 that if they tell you to round to 4 places, particularly for the standard deviation, that you follow those rounding rules pretty carefully. So let's go on to our next part and use this information to calculate a probability. So same context, same percentage. We're still dealing with a random sample of 90 children. That's important because if I change that 90, then I'm going to change my standard deviation and I'm going to have to start over with those calculations. So for this one, a sample of 90 children, what is the probability that at least 19% are overweight? Notice 19% is higher than our mean, and we have an at least, which means we're going to be shading above that 19%. Let's go ahead and take this to StatCrunch. And what I want to do first is modify my normal curve so that I have the information from our problem. Let's just double check that I got everything in there correctly. Okay, so we have 0.188 and 0.0412. And we are looking for the chance that we're above 19%. So notice when I graph, they don't display the mean number exactly, but 0.18 is in the middle. Here's 0.19. That gives me a probability of approximately 0.48. So let's look back at the context and see how we would interpret that, or what we could say. Well, our probability would be about 48% that at least 19% are overweight. Now, part of the reason we're so close to 50% is this 19% is pretty close to our mean, even in light of our standard deviation. One standard deviation above the mean, if we put our tick marks on there, is going to be close to 23%. Alright guys, so that'll be it for this video. We'll pick up and wrap up 8.2 in the next.